So it's certainly not the whole range of applications of stochastic programming, but I thought I'd give you kind of a view of different kinds of applications. So what I'll do is I'll go through sort of the basic setups and how they fit into stochastic programming. So the first thing I'll talk about is machine learning, which you can think of as some kind of forecasting. But you can view machine learning, I think I've said before, as a version of stochastic programming, or a version of stochastic optimization anyway. And then I'll talk about vehicle routing. I mentioned that before, like with emergency vehicles, where you put emergency vehicles like ambulances in different places. So I'll talk about those. I've worked in things for airlines. So this one is airline crew scheduling. So I'll mention that. I've done a lot of work in electric power, and I gave a talk about that yesterday in the economics department. But I'll mention some of those problems. Environmental policy. So this is things like carbon taxes and renewable incentives for renewable energy. So I'll talk about those kinds of things. I'll mention a little bit more about finance, and then a little bit more about revenue management. Okay, so that's the basic outline. So let's start with machine learning. So I have a colleague who's in machine learning, and he says machine learning and stochastic optimization are really the same thing. What you're trying to do in machine learning is to minimize the expectation of some loss of a prediction. So you're trying to fit some data and then minimize the expectation of that loss. So here's the way you could think about it in sort of a stochastic programming view. Let's say there's a set of features. So we have some observations. This could be features about people. Let's say we're trying to predict whether these people are going to buy something or not, or we're going to try to predict whether they're going to have an accident. Let's say we're trying to price some kind of insurance. So we have a lot of features about them. So if it was something like where I was trying to sell them something, like on the internet, the features would be everything that I can, everything that I know about that customer when they come to my website. So you know, I would know their domain. I would know their operating system. I would know perhaps if they had. Oh, this was not. Let's see. Maybe this one just. Oh. Not sure what happened. Yeah, it looks like it just, I don't know if it went to sleep or. see it. Okay. Yeah, my power went out. Okay, so we have all these features, everything that we know possible about that customer. And then we have classification, so we would see, did they buy or did they not? And so we would have all the customers that come to the website, and we would say, let's classify them as people who buy or people who don't buy. So the classification here, or a classification or the label that's associated with the features would be this variable y. So our observations would be, we'll see a set of customers who come to the website, and then we see whether they buy or not. And then what we want to do is to create a model with a set of parameters such that we minimize loss. So this is, our model has these parameters these parameters w, the features are x, and then the label or the classification of each of those features is y. So this is our loss. So there are a number of ways you could think about loss. One way is just, you could say it's the norm, the norm of W transpose X. Like, this would be like our prediction. We're trying to make this get close to Y. Say Y is 0 or 1, whether they buy or not. And we might try to make this get close to that Y. But in general, what we want is we want W that minimizes over the expectation, and this would be the expectation over all possible feature vectors. So this would be over all possible customers. But I only get to see customers who have actually arrived at the site. So, so my data are like observations. So it's like samples of the features, and then samples of the classification, or samples of the label. So I see samples of the features, samples of the label. But what I'm really interested in is to minimize this expectation. So you can think of W is like the first stage decision. And then whatever the loss is, that's like your second stage decision. And then, and that's just going to be whatever this loss value is. And then you want to minimize the expectation of that function. The way this is usually done is you set it up so that you say, I have a set of observations, and I'm going to take some of those observations and use them as a training set. So I'll take some observations, and then let's say I'll minimize the sample average across that training set, or I'll take the training set and then I'll just apply that stochastic gradient algorithm to it. And I'll use the stochastic gradient throughout the training set. And then I'll see how that performs on a validation or a testing set. And the idea of using the validation set is that this is some data that you've held out. You're going to test it on that validation set to see how well whatever W you've come up with, to see how well W performs out of sample. And then often what you want to do is pick a W that performs well on the validation set relative to the training set, because you don't want to overfit. So you try not to overfit the data and come up with a best set of parameters. Okay, so just a little bit more. So we could say, let's say, to determine if customers are buyers or not. So we could say they're either, if they're a buyer, y is a 1. If they're not buying, then y is a 0. Often we'll use some kind of linear predictor. So we'll say my prediction is going to be based on some parameter. I'm going to try to base it on some set of parameters, w times x, w inner product with x, and then plus, let's say, a constant coefficient here, w0. And then my loss function, this would be like I'm trying to fit something that goes from 0 to 1, so I'll come up with something that looks like a likelihood, like this would be a probability that y is 1. So 1 plus the expected value, or 1 plus the exponential of the product of w transpose x, w0, and y. So if y is 1 and this is getting something close to 1, then that's exponential minus 1. And if y is minus 1 and this is predicting something close to 1, that would give me something like exponential of 1. So I'd get a higher value if I don't match w transpose x, w0, and y. So we'll often have something like this. This would be our loss function. But you could think of this as, this would be like your second stage. So you make decisions w in the first stage, and then in the second stage you have this that you want to minimize over all. You'll have like the sum of all these over all the possible x's and y's that you've observed. So all those will go into your solution set. This also, you can also apply this for something like using a deep neural net. So you might like have a deep neural net where you have multiple layers of sort of predictors. And on each layer of your predictor, you'll take the result of the previous layers. So you'll start off with just x, say. And then on every layer, you'll have, again, a set of multipliers, w's that you're determining, that multiply by that x at that layer. And then you add on, let's say, a constant. And then you take some transformation. Usually the transformation is either just the maximum of 0 and the value. In other words, just like an indicator of the value, or else 0 if it's negative. Or some kind of exponential, some kind of logistic, like 1 over 1 plus an exponential of minus the input x. So you'll take this transformation, and then that will be your input to the next layer. And then you'll take another transformation, that will be your input to the next layer. And so you'll end up, kind of the reason that neural nets work so well is that, well, they're highly nonlinear and they're able to represent a lot of different kinds of relationships. But you could still think of optimizing over these w's. Optimizing over these w's is still the same kind of process. It's still like I make a decision about the w's, then I get to observe my data, and then I pay the loss. I make a decision about the w's. Now, in this case, I'll have to transform them to get them into my final prediction down here. The final prediction would be the last output of the last layer. And then that's my final prediction. I'll find out, well, how far is this prediction from my observation? And I'll do that for each of the different observations that I have. Again, what's often done in these deep neural nets is just a stochastic gradient algorithm. So you'll basically take gradient steps for each of the components of this this composite function here. Because x is like xj is a function of xj minus 1, which is a function of xj minus 2, so on down to the beginning x. But yeah, the point is, this is also like a stochastic program. So this is like the second stage of a stochastic program, where you're just defining this distance measure as your loss function. And as I said, that stochastic gradient algorithm is usually the standard that people are using. So you can use the stochastic gradient algorithm for that as well. I think one of the things that stochastic programming gives you for problems like this is that it actually gives you a range of different things that you can optimize over. So most of the time, a lot of these loss functions that people use in machine learning or neural networks, a lot of those loss functions are just like hinge loss. Like if I'm below estimating it, it's not bad, but if I'm above, I'll get a linear penalty. Or absolute value, like I had. But there's a whole range of things. So you can think of the loss as like these risk measures, like all the possible ways in which we talked about risk measures. And often it makes a difference how far away you are from the prediction. And so these risk measures in particular can protect. So if my y was, if I was trying to estimate not just whether people buy something or not, but for insurance, how much it's going to cost me for selling insurance to a given individual, what I'm really worried about is the tail. I'm worried about very heavy losses. So I may want a risk measure that is focused on how likely it is that I'll have very, very heavy losses from a loss associated with an individual that's very high relative to the mean. So you can use any of those risk measures that I talked about earlier. You can use any of those as loss functions. And so if I wanted like say R of W is the overall risk of making choice W for the entire population, and what I'm going to do is, for the stochastic program, maybe is to minimize the sample or the empirical risk. That this would be the set. Let's say I had n observations. This would be the risk over those n observations. So I might use the risk over those n observations as my to measure how far you are when I use RNW, how far I am from RW. And a lot of that's due to this Vapnik and Chervonenkis. And basically, they say we can measure things in terms of what is sort of the dimension of the class of functions that can be defined by W. So this is kind of how big a set can the set of functions that's defined by W, how big a set is that? And that's going to give us, this can be used to give us a bound on how far away an estimate with this empirical measure Rn is from the true value R. And so their result is the one I have down here at the bottom. With probability, with a given probability at least as high as 1 minus eta, so eta is 1. Eta is just a parameter in here. With the probability at least 1 minus eta, I know that the worst case, so the worst case over all the W's, so what this dW is going to do is it's going to tell me something about what happens in the worst case. So the worst case over all the W's that I might try to estimate, if I look at R of W minus Rn of W, that's less than or equal to something that's the order of the log of 2 over eta divided by 2n. So it's going down by 1 over n here. And then the log of n over this dW. And then something that's, so that this part's kind of small. That's this log term. But what's affecting it most is this last term. So most of this is based on this, that it's the size of the set of functions that you can get from W divided by n to the square root. So basically what that says is the worst case is going down at a rate of 1 over the square root of n, which is like the just like the central limit theorem. So this is saying my worst case error is something like the central limit result. It's something that's related to 1 over the square root of the number of samples that I have. So it's like 1 over the square root number of samples, and then this dW is kind of how it scales in terms of the class of functions W. If I just have like 2 parameters of W, then W is like 2. But if W has many, many parameters, then this value gets bigger. So I can get bounds on this, on the maximum deviation that I have here, on the basis of what this W is, and then everything is, again, scaling by 1 over the square root of n. Okay. So that's a little bit about these machine learning problems. Just some observations about it. As I said, if you have if you use all of the sample set, then you may end up overfitting the data. And in fact, what people see in practice is that as you have more and more in your training set, the error actually sometimes you may have more and more overfitting. So in some cases, it may be good not to use all your data. In other words, let's say I have 100,000 observations, and I start to go through the data, it may be best to stop after 50,000. It may be best not to use all the data because of the potential for overfitting. You can test this by taking taking the result from your training set and then testing it on the remaining part of the data. But what we'll often see is that as you go through, like if I apply stochastic gradient to a large data set, I may decide that I'll only go halfway through that large data set, take what that last result is, and then use that to try to, or use that on the remaining part of the data set to test how well that performs. And often it performs best if I stop somewhere earlier than getting through all the data. What it also seems is that it may actually be faster when we have large training sets. It may be faster to stop on those rather than using smaller data sets. That is, the larger the training set, the earlier you may want to stop. So it may be faster to do things, but you may be able to get to a good solution faster if you stop earlier. That's kind of the bottom line of that. And I think what's kind of surprising, and I'll show on the next slide, that even though we could do more complicated optimization methods like quadratic methods or second order methods like Newton's method, you could try to use Newton's method on these problems. You could try to estimate like second derivatives. But it turns out that often those methods perform worse. So the simple stochastic gradient methods often perform the best out of all these. So I'll show those on this slide. So here's, this is just some observations. So think of SA mean stochastic approximation. Those would be like stochastic gradients, stochastic quasi-gradient methods, etc. And this would be sample average approximation. This would be, so if I just use stochastic gradient, all I'm using is a single observation, and I'm taking that observation, and I'm saying, does what I get from this observation, how does it change the parameters that I have? And I'll take a step in that direction. If I take lots and lots of observations together, then I can start to estimate things like second derivatives, and I can use higher order methods like Newton's method by estimating those second derivatives, or at least estimating gradients, like getting more information on them. Or I could do some combination. I could take a bunch of data together and use that to kind of estimate a direction of descent. Or as I said, to estimate lots and lots of information and get these second order methods. But what we often get is what I've illustrated over here. Is this is the number of iterations, and this is the error. And this is LBFJS. So this is the BFGS approximate. It's an approximation to the BFGS. That stands for Broyden, Fletcher, Goldfarb, and Shano. And their method is what's called it's a quasi-Newton method. It is a second order method where you try to estimate what the Hessian matrix, what the second derivatives are, You try to estimate that by taking gradient combinations of gradients. So you sort of say, oh, I've got a gradient like this, I've got a gradient like that, put them together, and that gives me an estimate of what the second derivatives are. So this is a second order method. So in general, that blue is a faster algorithm, much faster algorithm for deterministic optimization. It's a much faster algorithm than stochastic gradient. However, on a lot of these problems, what we'll see is that stochastic gradient does much better for low numbers of iterations, does much better than these second order methods. The second order methods take a long time for you to get enough information and for you to get close enough to an optimal solution for the method to start to improve, for the method to actually start to get better. You can see that it's getting a little bit better. You can sort of see the red line above the blue line down here. So eventually, if you have enough iterations, the second order methods end up better. So this second order method ends up eventually better than the stochastic gradient. But as I said, it's often worse to overfit the data on many of these problems. So it's often best to stop somewhere in here. So you may want to take the stochastic gradient and then stop at some point. And at this point, you're doing a lot better. So the error is a lot lower with the stochastic gradient than it is with these second order methods. Bottom line is, it looks like stochastic gradient on machine learning, deep neural network kinds of problems. Stochastic gradient seems to be the method that works the best. And in particular, that it's good not to use all of the data that you have. If you have lots and lots of observations, it's good not to use all of it to try to fit things, because you may end up overfitting, and that's a danger in these kinds of problems. That I get. I'm just fitting noise, basically, and we don't want to just try to fit noise. Okay, so machine learning is a big application. I think that's one area where stochastic programming has a lot more potential. Now let me talk about a few others that I'm familiar with. Okay, so this one is vehicle routing. So the case that I was working on was a company that transports, does like within-day delivery. So if somebody wants to get something delivered from one part of a city to another part of a city during the day, then they'll make those deliveries. And it was more commercial. It was like for production, manufacturing people. So there were trucks. So you had trucks that would go pick up a load at one place and then take it to another part of the city during the day. So one of the big things about it is what you'd really like to do is to have these vehicles always move with a load. So they pick up a load in let's say they pick up a load in the western part of a city. They transport it to the eastern part of a city. And then what you'd like is that they get another load in that eastern part and take it full to the next part. But it could be that there's nobody who's asking for deliveries from the eastern part where you've just taken the truck. So you may end up wanting to move that truck to a different location where it's more likely to get a request. So what you're doing is you're taking the truck from one location and then moving it to another and wanting to minimize the total time it takes to deliver all the products so that you can increase demand. Or minimize the cost of meeting all the demand that's there, where the cost might include some delays or extra time for the vehicles. But the main thing you're trying to, the main sort of goal in this is that you don't want vehicles to have to do a lot of empty moving, because if they move empty, then you're not receiving any revenue from that. Now, in all these problems, particularly in these within-day problems, you don't, like in this company, they didn't know tomorrow's demand at all. They don't know what tomorrow's demand is going to be. They just have what yesterday's and the day before's demand. So they just have observations of what demand was in the past, and then they're trying to make those decisions about, well, where should I start my, where should I put my trucks at the beginning? And then once a truck delivers a load, where should it go next? And so it's always about, it delivers a load, where should it go next? Or it could be that you decide not to take a load, but particularly in this problem, it was the decisions were where you put the vehicles at the beginning and where they went after they made a delivery. And then you minimize the total number of costs. So I solved a bunch of problems here, different numbers of sites where the vehicles could be. So the vehicles might have stations throughout the city where they could be located. And then they could make different numbers of deliveries. So if they could do 4 deliveries in a day or 5 deliveries in a day, that would be the number of stages. So the number of stages were, a stage was basically a delivery for every vehicle. So if it took an hour and a half, say, to make a delivery, then in 4 hours, or they could, in 6 hours, they could make 4 deliveries, or in let's say 7.5 hours, they could make 5 deliveries. But those would be the stages. So the stages were each of the deliveries. So they would make a delivery or not, or move to another place, and then wait and see what the demand would be. So we took samples of the demand, and we got we could sort of filter the samples. Either put in all the samples. Maybe we had a few hundred samples, but then you'll get huge trees. So if I have 30 samples, 5 stages, that's like 30 to the 5th. So we've got 30 to the 5th, 75 to the 5th. These become very, very large problems with the number of vehicles. So number of vehicles makes these problems get very, very large. But the algorithm we used to solve this was this abridged nested decomposition algorithm. This algorithm that creates those cutting planes, the bounds on the value function for each of these stages, 4 or 5 stages, and goes through the tree, goes forward, making decisions, and then goes backward, creating cuts. And forward, making decisions, backward, creating cuts, and keeps on doing that until it gets, until it tests for convergence, and it says, it tests and says, okay, now I think my upper bound and my lower bound are close enough, and the algorithm stops. So I'll show just, these are some results. So this is with a fleet that had 140 trucks. So there were 140 vehicles, and this is 16 locations. And I was comparing this to that standard algorithm, this what's called the SDDP algorithm, stochastic dual dynamic program. And basically, the stochastic dual dynamic program wasn't able to complete on these problems. But by using the sort of the more the efficient implementation in this abridged nested decomposition algorithm, the abridged nested decomposition algorithm was able to solve this in relatively short order. So I mean, these still taking 10 minutes, 5,000 seconds here. Or is it CPU seconds? Yeah, CPU seconds. Well, it's taking it, I guess it's taking more than 5 minutes. I guess it's taking like hours. But at least it's able to solve these problems. So with this abridged nested decomposition, we're actually able to solve some of these problems with relatively large fleets. And links would be this like the number of different routes that the trucks can follow. So a number of different ways that they can go from one point to another. Okay, so you can solve problems like this. So problems like where we're routing vehicles through a network, those are perfect applications of stochastic programming. Okay, now the vehicle routing it's a problem that should be integer. So in general, those vehicles have to satisfy integer constraints. With 140 vehicles, we almost never had to do branching. So most of the time, the solutions would end up being integers anyway. So when you have lots and lots of vehicles, you end up with integer solutions. So so we didn't really have to consider the combinatorial nature of these problems. The next problem I'll talk about is one where you really have to consider integers because they end up being very discrete decisions. Well, the decisions, in this case, the decisions are numbers of vehicles that go from one place to another. And in the next problem I'll talk about, the decisions are really whether crew does one thing or another. So they're all 0, 1. In this case, it was number of vehicles, so it was like anything from 0 to 140. So rounding didn't make that much of a difference. But in the next one, everything's 0, 1. Okay, so this is airline crew scheduling. So the idea in airline crew scheduling is you have a set of crews, and the crews are both the cabin, which would be the flight attendants, that's the cabin crew, and then the cockpit, which are the pilots. So the way airlines work is what the airlines do every month is they come up with a schedule they come up with a set of schedules. A set of schedules for a crew to follow a given trip. So they go on a given trip through different cities, taking different flights. And some of those flights could just be to go from one airport to another. So it might be that somebody goes from Delhi to Lucknow. But then their next flight is out of Kolkata. And so they'll have to take a flight from Lucknow. I don't even know if there's a flight from Lucknow to Kolkata. But they'll have to take a flight there in order to get on the next flight where they're actually a working member of the crew. And then they'll be on the working member of the crew maybe for the next flight. So they put a lot of these schedules together, and then the crews basically pick them sequentially to determine which person is actually going to be on which of these crews. But the question is, where should the crews go? So how should you lay out the crews? What you'd like is that they don't spend a lot of, you don't want them to spend a lot of time sitting on another airplane as a passenger. That's called deadheading. If they're deadheading, they're a passenger, they're being paid, but they're not doing anything. And you don't want them sitting in airports for a long time, again, being paid and not doing anything. So you'd like them to be on the planes working as much as possible. However, they also have rules about how much they can work. Like pilots can't work too long, and they have to have rest. So there's lots and lots of practical issues that they have to satisfy to put these schedules together. So airlines spend a lot of time on this. They work on it. Each airline, so they do this basically once a month. So they'll decide what the crews are going to be for the next month. But each airline spends a huge amount. So they probably have 5 or maybe 10 people who are just doing that, just coming up with what the schedules are going to be for the next month. The problem is, and so this is where the stochastic programming comes in. So airline crew scheduling has been around for a long time. And as I say, because it's it's the second biggest cost for the airlines. Fuel is their biggest cost, and then crews are their second biggest cost. It's about 25% of their revenues. So if they can save money of that 25%, if they can use optimization to save 5%, that's going to be worth a lot to them. So that's can be like $1 billion. So it could be $1 billion a year to solve these crew scheduling problems. So they're worth a lot of money. But what happens is there may be delays. So there could be delays because of weather. That there's a storm that hits an airport and then they're not able to fly in. But those disruptions get moved through the schedule. So for example, I was doing some work for Air New Zealand, which doesn't have a lot of planes, which was part of the reason why we were able to study them. But because they don't have a lot of planes, any single disruption can affect their entire system. So they had a pilot who had, when I was there working with them, they had a pilot who had flown to London. So he'd flown from New Zealand to London, and then he got sick. And so he couldn't fly the plane the next day. Well, they didn't have an extra pilot in London. They had to fly somebody from New Zealand to London, and that made the flight completely late. But that meant that plane was supposed to pick up passengers in Auckland, so that flight was late. Then that meant that the flight from Auckland couldn't take off, and the crew that was supposed to be on the flight to Auckland, they couldn't go to their flights. So the crew was stuck there too, and the flights that crew was going to work on. So that one guy getting sick ended up disrupting maybe a dozen or more flights, just because one person gets sick. So that changes everything that happens in these crew scheduling problems. And what we wanted to look at is, can you plan better if you think about these uncertain things that could delay your flights? Okay, so here's just to show you the setting. I have a little example. So this is Chicago, O'Hare. This is Detroit in the US. So Chicago, Detroit, and ATL is Atlanta. Okay, so what you might think of is, suppose there are flights that go from Chicago to Detroit, and from Detroit to Chicago, and from Detroit to Atlanta, and Atlanta to Detroit, and Chicago to Atlanta, and Atlanta to Chicago. And suppose I have a plane that goes on, and that just does those two flights. So it goes, the plane does Chicago to Detroit, Detroit, Chicago. And this plane does Atlanta to Detroit, Detroit to Atlanta. And this plane does Atlanta to Chicago and Chicago to Atlanta. So if I have a crew that takes if I have a crew that takes a trip that goes like this and this, suppose this is so a crew that follows. In other words, if I have a crew that follows the plane, then if this flight gets delayed, the only thing it's going to delay is this leg over here. So if the crew goes with this plane, then if this one gets delayed, it just affects this. However, if the crew is going to, so this would be like this crew, and then maybe this is another crew. But if I have a crew that goes all the way around, and another crew that goes all the way around, then if this one gets delayed, it's going to affect, because this is the same plane, it's going to affect this. But that means also that this flight is going to be delayed. And then that means if this flight is delayed, this flight is going to be delayed. But if this flight is delayed, this one's going to be delayed. So if I send my crew like this, as opposed to this way, a single disruption can make everything late. It can make all of the other ones late. So depending on how whereas over here, if a single disruption just makes two flights, that flight's automatically late, and then it'll make the other one late. But over here, if I send my crew in this routing, then a single disruption makes all of the flights late. And you'd like to be able to avoid that. So the idea in these crew scheduling problems is what we'd like to do is to make decisions about, let's say, minimize the cost of assigning all the crews, or assigning crews that cover all the flights. What you want is I'll assign crews in such a way that I cover all the flights. Each of the trips, or they call them tours of duty, each of these tours of duty of the crews has to start at some place, go around, and come back to that place. Each of those tours of duty has a certain cost, so I minimize the cost of each of these tours, subject to the fact that each of these tours is going to cover, so AX equals B says that they cover all of the flights. The tours, either they're flown or they're not, so it's either 0 or 1. So in this case, integer makes a big difference. So the integer variables make a big difference. And this is my script Q in this case, different font. I minimize the expected cost of all of those disruptions. So if I have this crew, then I'll minimize the current cost plus expected cost. And doing this relative to deterministic, you can, again, save about 10%. So we showed with Air New Zealand that so the way they were basically solving it is just ignoring this part, ignoring the expected cost after disruptions. But by ignoring disruptions, they were creating a lot of opportunities for losses, or for the sort of these cascading kinds of delays. But by solving this problem, we were able to reduce costs about 10%. So, yeah, so stochastic programs can have a lot of value for these kinds of problems. Okay, now, all right, so this one is one where you really can't ignore the integer variables. So the integer variables are very important. And what we showed when we were solving this is what made a difference is whether you wanted to do branches with the integer variables such that you minimize the number of times in which a crew didn't follow the same flight pattern as a plane. You wanted to keep crews on the same plane. That was basically, and we used that to make the integer branching tree be more efficient. So the paper on this problem, which is in the journal Transportation Science, that uses kind of an efficient branching mechanism based on having crews follow planes. Okay, so that's vehicle routing. Now I'll talk about another problem which I talked about in the economics department yesterday. This is stochastic unit commitment, and that's a problem from the electric power industry. And this is a big issue because electric power is such a big part of every economy. It's usually about 5% of every economy. So if it's 5% of the economy, the stochastic unit commitment problem is estimated to be, well, solving it correctly can be 5% of that. So so what is that? It's not quite 0.25% of the whole economy, but it's a lot of the economy. I mean, you measure the value of this model in terms of billions of dollars in every country. So what does it do? The unit commitment problem decides what generators are going to be used to generate electricity and how much they're going to generate. And the basic idea of those generators is you want to meet the load, that's the demand. So you want to satisfy the demand, and you want to maximize or maximize surplus. In other words, either minimize cost to meet the demand or maximize whatever revenue you collect from the people paying for the demand minus the cost. Now in the past, what people were doing is just solving these deterministically. So just saying, I have a forecast of what I think demand's going to be. I have a set of plants. I know how much each of these plants costs, or people have told me what they cost. And then I take all that data and I optimize. I minimize the cost of meeting all the loads. But in reality, what happens is there's both uncertainty in demand. We don't know exactly what the electricity demand is going to be. And there's uncertainty in supply, particularly because of renewable energy. So things like wind and solar energy are very variable. They're very uncertain. So there's a lot of uncertainty about what that supply is. So because of these renewable resources, there's so much uncertainty in the availability that, well, at least I think it's really necessary. I think, I can show in models that we get a lot of value out of adding in, because it has a lot of advantages. It sort of has utility as its basic principle. It considers uncertainty as a whole. It hedges against randomness, it requires some input in terms of the distributions, and it can be computationally hard, but we can still solve these problems. In order to solve these problems, we have to generate these scenarios. So for a lot of this work, I had to focus on generating scenarios of wind, and generating scenarios using Markov chains. So if the wind is at a certain rate in certain places, then we'll see, well, how likely is it that we'll have wind in the next hour in the same place or a different place. And using a lot of different scenarios to try to come up with these decisions. So the way to look at these models is basically what I want to do. Oh, these also are integer because I have to turn on some of these plants. Either I turn them on or turn them off. So I have costs for fuel. I have costs to start up these plants or shut them down. There could be costs associated with shutting down a plant or starting a plant up, or a cost of the fuel that's associated with running the plant. And then if I know it happens here in India sometimes, where the power company just isn't able to supply, and they decide to shed load, which means that they are just not going to serve the demand. So that means you'll have a blackout for a certain, or a brownout, reduce the power for a certain amount of time. So that's the kind of thing that electric power providers try not to do, but if they have to, they will. Yeah, so it's sort of a necessary evil, but we can put that in and say that there is a penalty associated with that. So the decision variables in the first stage are whether units are on or off, and then the second stage you're deciding what units are on, and then the second stage, let's say, after realizing what the wind is or what the solar power is, and what the generators are capable of, we'll decide how much we're going to generate for from each of these plants. The constraints are, so we have to meet the electric power laws like Kirchhoff's laws. So we'll have some kind of balance to make sure that we meet all the laws of how energy is going to go through the electric power network. Then these would be constraints on how the generators are run. They're only allowed to be up a certain amount of time or down a certain amount of time. They can only ramp up at a certain speed, that is, increase their generation at a certain speed, or down. They may only be able to decrease at a certain speed. And the lines have limits, so they can't go beyond a certain amount. And the generators, of course, have limits. And then you often want to keep a little bit of generation available in case something catastrophically fails. So there's what we call reserves that take care of that. Okay, so we can solve this again with multi-stage stochastic programs. So this is just the general setup of a multi-stage stochastic program where I've put everything together like this, and what I often will want to do on problems like this, I want to decompose them as much as possible. I'd like to decompose it down to the individual plant. So then I just decide for each individual plant what they do, how much they produce at every point in time. So that's the overall goal of these kinds of problems. So this is what a formulation would look like. So the U's are decisions on how much, what my control is, whether I turn something on or off. So U is a decision on whether generators are going to be on or whether generators are going to be off. And then if they're on, then I'll have some cost for running them. So depending on how much they're generating, that will be my cost. Because I have these constraints that say I can't turn things on or turn things off, I have some costs associated. If I try to shut something down or turn it on, I might have those startup and shutdown costs here. And I'll have different things that go into, like this would be different parts of the second stage, that go into how much wind I'm going to be able to provide in power. And then I also have the probability of each of the scenarios, and then what's going to be generating, number of time periods, and other kinds of technology. I think this is just showing it in a little bit more detail what all the technology constraints are. I guess the important thing is the one that I've highlighted down here. What we try to do in these problems is to set them up with explicit non-anticipativity constraints. So I explicitly say that if two scenarios have the same information, then they must have the same decision on what the use are, what the on and off decisions are. So for two scenarios that share the same information set, I have to make the same decision. And then what I do is I relax this constraint and put it into the objective function. So I use that Lagrangian approach of relaxing the constraint and putting it into the objective function and optimizing those. As I said, this kind of problem that we can solve for thousands of generators because we can split them up effectively into each scenario and each generator. And then I just have to look at one generator at a time and decide for each of those generators what they should do. Okay, now the next model I'll talk about, or the next application, is this one in energy policy. So the problem here is that what we want to do is we want to see what's the impact of some kind of, let's say, carbon tax, like a tax on CO2 production, or some kind of quota. So if I say that each country is going to be limited to a certain quota, let's say I go back to whatever the CO2 production was in 2010. And let's say I say that every country has to get within 5% of their 2010 carbon emissions. So that would be the constraint in here. And what the model does for this, this policy analysis is it has, for every region of the world, it models the energy sector of that region and how, like, that would be basically how does that region get its energy, and how does that energy, like how much is electricity, how much is natural gas, how much from oil, and then how does it use that energy as part of its overall economy. So there's one part of the model that says this is what the energy sector is, and it has all of the different technologies that that country might use for generating energy. And then it has a model that tells how does that energy how is that energy used in the rest of the economy. So, and the rest of the economy is basically just saying there's labor involved, there's some capital that goes into it. So everything else is really very, sort of very high level. So this is everything else in the economy is just like capital, investment, labor, and then energy, including electricity. And so there's a model of every country in this global model. So the global model has a model of every country, their non-energy sector and their energy sector. Now the reason for this for stochastic programming in this model was to try to assess the effect of different incentives on investment. So you might provide incentive for people to put in renewable generators. So if you put in an incentive that said people are going to get a payment for putting in a renewable generator or a tax advantage for putting in renewable generation, how is that energy investment going to be returned to the economy? And so the uncertainty in here was what is the effect of that energy investment on the growth of the energy sector. So we looked at how does the energy investment affect the growth of the energy sector. And we described it in terms of either a high return for every kind of energy investment you could make. Maybe I get high return versus low return, because I don't know exactly what the return's going to be on these investments. So do I get high return or low return? And by putting in uncertainty in terms of the high return and low return, what I get is a portfolio of different investment types. Whereas a deterministic model will just pick one kind of investment. So the deterministic model just says, oh, this investment is better than the others. It decides on that. Whereas the stochastic model picks a portfolio of these investments. Just sort of pictorially to see what the stochastic model does, it's looking at, I make investments in the first time period, I get high return or low return. Next time period, high or low, and so on, high or low throughout time. So it constructs these, it constructs this tree and then optimizes over the tree. And what we were able to show with this model is that, again, if you base decisions totally on a deterministic model, you would lose something like 1.5%. Let's say we decided that we wanted to cut carbon to year 2000 levels. You would lose 1.5% of global GDP if you based that kind of policy on a deterministic model versus a stochastic model. So the stochastic model, again, has a value that's now, in this case, measured in many billions of dollars. So in terms of what those investments might be. So you can do much better by investing with something that's stochastic relative to something deterministic. Okay, now I have, just to make a little bit more specific on these financial models. So financial models, often these investment models have two parts of the objectives. So you could think of this, again, I'll make an initial decision. So my first stage decision is how much do I invest in different assets? So that's my X. And again, let's say W here is my random variable. So how much do I invest in these different assets? And then I'll realize whatever those returns on those assets are. And then take the expectation. But my overall objective is going to have something to do with risk. So if I'm minimizing, it would be something to do with risk minus something to do with reward, which would be the expected return of my investments. So for portfolios, it's often minus the mean of the return of the portfolio plus some risk aversion parameter times, let's say, the variance. This would put it into a quadratic program. Okay, so often we'll have uncertainty that affects the return. It could be that we have uncertainty in the risk that I don't actually know how risk averse I should be or how risk averse people might be. But in general, there's going to be some uncertainty that's affecting the mean and uncertainty that's being represented here in the variance. Just to see in a little more detail, the kinds of decisions you would make would be how much do you hold of each of the assets at a given point in time, and then what kind of actions do you take? So at every point in time, you'll have to sell some of the assets and then buy some others. So I'll take actions to sell and actions to buy. When I sell and buy, I'll face some kind of transaction cost. So in this case, I'll have a transaction cost here that's represented by tau, which is how much do I lose when I buy something, because I'll have to pay a little bit more than just what the posted price might be just for the transaction. So there's a proportional transaction cost in these models, and then I'll have this return. This is the uncertain part. Then I'll have the return that's associated with it. And then my objective is the utility of, let's say, this would be my expected return over time. So maybe it's my return is like the log of value at any point in time. So it'd be like my return on investment X, given that it's returned all this, these revenues over time. And that will give me my final wealth. So this would be my final wealth in here, and then it would be I want to maximize utility or minimize negative expected utility. And then my value at any point in time is actually just 0, unless if I'm feasible, and otherwise it would be infinite. So I just make feasible decisions about how much I sell and how much I buy at each point in time. And then I would optimize the value function here. So it's the value function of being in any state, taking the best possible control, being feasible in the next state, and then the value to go from that state on. And then I can represent with linear constraints, starting off with whatever I had before, the return that I got on it, and then however much I sell, where I have to pay a little bit more when or have to lose a little bit more when I sell something. And how much I buy. And then that's going to be the amount, when I buy, I get a little bit less back. And that's going to be the amount that I put into the next time period. Okay, so this just gives you a specification in that multi-stage setup of how these financial planning problems are organized. Okay, now the last application I'll talk about is network revenue management. So network revenue management is things like I've got a set of seats on planes. So H here is my capacity. And that's going to be the available seats that I have. Let's say it would be the available seats on all the flights in my network. So this would be all the flights, say, for a week. And then I'm going to be selling those seats. And the sales correspond to these X's. So X would be that I sell a given itinerary, which might use up, like it would have maybe a couple of different flights on it, and that would use up seats on 2 different airplanes. So if I go like I'm going to go from Lucknow to Delhi, Delhi to Chicago, I'm using up the Lucknow to Delhi seat, and I'm using up the Delhi to Chicago seat. So when that seat gets sold, it uses up 2 of the resources in here. And then the way I have this set up is that this would be like my slack variables. These are my decision variables associated with whether I'm going to sell a seat or not. So I decide whether I sell one of these seats or not, and then I minimize, again, it would be like maximizing the total revenue that I get from selling these seats or not. And then the way I keep track of things is I say, well, I can't sell any more than whatever the demand is. However, if I try to sell more than the demand, I'll penalize myself so that I subtract off whatever it is that I would have earned. So the Y, I might say, okay, I'm going to offer this seat for sale. So X says I'll offer the seat for sale, and then Y says, well, actually, you can't sell it because you didn't have the demand. So Y is the recourse action that says, if you didn't have the demand, then you're not going to realize that sale. So it has this format of a recourse problem where I make decisions now about what seats are going to be available. So that's what the X is. X is going to be the number of seats that are going to become available. And then my recourse decision is, well, if I said I'm going to book my revenue for those seats, but if I didn't have enough capacity, or if I didn't have enough demand for selling those seats, then I'm going to have to subtract off the revenue for that demand. So these decisions represent the amount that you're going to be able to sell, and it's the structure in those problems that allows us to solve those very, very large vehicle routing problems. Putting stochastic programs into those crew schedules adds a lot of robustness to the schedule, and that actually creates a lot of opportunity. And stochastic programming adds to these unit commitment, these electric power problems, smooths out the schedules, and actually reduces issues that people have with prices in these models. And as I said, it leads to diversification that's important in those policy models. So hopefully you've gotten a lot about stochastic programming from these few days. I think what are the things to remember? What stochastic programming does is it provides a very general framework. It applies to any kind of decision making under uncertainty. It's that very general framework that allows it to fit into a lot of different applications and makes it a versatile kind of tool. It uses a lot of results from different fields. So if you like mathematics, or like I do, and Joydeep does, you get to use a lot of different things. You have convex analysis, optimization, and probability. And there are a lot of challenging issues, a lot of different things you can do research on. So lots of challenging issues, and a lot of applications to work on. So I wish you all the best in stochastic programming and for all the work in your dissertations. Thanks, Sam. Okay.
He's going to take photos. So,
Oh, okay. Oh, he's got it.
call upon Chamanlal Devangan from IIT Kanpur.
All right.
I call upon Kiran Kumar from Pondicherry University. I call upon Amit Kumar Gupta from IIT Delhi. I call upon Jagannath Patra from IIT ISM Dhanbad.
Hi.
I call upon P. Ponraj from NIT Trichy.
Hi.
I call upon Anjan Kumar Dan from IIT ISM Dhanbad.
Hi.
call upon Manish Kumar Mandal from IIT BHU.
Hi.
I call upon Rahul Singh from IIT BHU.
Hi.
And I call upon Thiresh Kumar Nayak from IIT BHU Varanasi. He's absent.
Oh.
So you can take it.
Okay.
I call upon now, it's time to, it's very important to thank the people who had supported us. So I would first, it would not be a good idea not to first say a hello to my, thanks to my two PhD students, and excellent PhD students, and I'm proud of them. I call upon Punam Kesarwani to come up. No, I am genuinely proud of you guys.
Puna.
And then I call upon Tanushri Pandit to come and collect her. Anirban Banerjee is from IME Department of IT Kanpur. As far as I know from his PhD supervisor, he is also a brilliant student.
Hi.
Devesh Shukla from IT BHU, Varanasi. So these are all part of the IT system basically. It's good, a lot of people from the IT system is coming. Pawan Kumar Mandal, IT Mandi. So when are you inviting us to that beautiful, he lives in a hill station actually.
Yeah, he told me.
Yeah, so when are you inviting us to Mandi? He lives more wise than that. I told him to invite him. Invite me to Mandi. Devendra Kumar Pathak from IIT Delhi.
Hey.
Bablesh Kumar Jha from IIT BHU, Varanasi. Have you been to Varanasi?
No, I haven't been to
That's a
Varanasi.
very
Yeah, all the
important
people
place,
from
yeah.
Varanasi. Thank you.
Vishwa Prakash Jha from NIT Trichy.
Thank you. Hey.
And then Firoz Ahmed from Aligarh Muslim University, which is also a central university and has a strong group in optimization. Over a couple of people
Okay.
work in optimization theory. You're from OR, right? OR department. So he's from OR.
Thank you.
So that's left for exams. So thanks to all of you for this, for your taking your trouble to come here, and hope you will enjoy. You can fill in the feedback form and we can have tea. Now we have to have a group for outside and then have tea also.
All right.